Okay, good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes. My new topic will be uh, it's a so-called savings on the electric bill topic, and this is good for all home users. Okay, let's proceed. My topic for this afternoon will now be on how to save electricity in our home, and this is good for all of us. Okay, so for those who would like to avail of this concept on how to save electricity, this is for you guys. Okay, let's proceed. The subject matter will be a long video format topic, and the title of the topic will be plug-in power factor capacitor. Plug-in power factor capacitor is just a capacitor. This is a capacitor. So if we plug in this one, we could avail of the services of this one. So this is the one that I will be discussing this afternoon. And this is good for all home users. Okay? It is something like this. So the concentration of the subject matter for this afternoon will be on how to compute for the capacitance of this one, such that if we try to use this one to a specific load in our home, okay, we could decrease the current consumption of that specific load. More specifically, if that load is a motor load. For a lighting load, we do not need this one. But for a motor load, which has a reactive power component, we needed a capacitor to counteract that reactive load. So we could lessen the reactive load for the motor or totally eliminate. Okay, let's proceed. So this is actually a capacitor for power factor correction. Okay, so I made this one with the plug already. So if we try to use this one, we just plug this one onto the outlet to that specific motor load in our home, and we could actually decrease its current consumption. And if we could decrease our current consumption, of course, our bill will be lesser. Okay, let's proceed. We needed the capacitance value of this one. Capacitance. Because if we try to buy something for us to use, we should specify the capacitance value, and it should be in microfarad. Microfarad is actually with the multiplier times 10 to the negative 6. Okay, let's proceed. Okay, I got my eraser cloth. So the title of the topic for this afternoon will be plug-in power factor capacitor. Okay, the problem is something like this. For you guys, this is for any home user which is watching my YouTube channel right now. Given, supposing we got a load here, an air cleaner with EUV. Air cleaner with EUV, it's an air cleaner. So it got a motor, right? And we would like to decrease the current consumption of this one such that, so that we could, lessen our electric bill. So if we try to bring out the diagram, this will be the utility line, 120 volts, 60 hertz here in the USA. This is the air cleaner. Of course, it's plugged in, right? So the circuit diagram will be something like this. And as an example to this, I uploaded already the actual explanation of this. Okay? The air cleaner that I'm repairing is the one on my last long video format. Okay, the air cleaner. I monitor the current consumption of the air cleaner to be 0.55 amperes. and the power factor is 0.62. 0.55 amperes is not so much, but I am not satisfied with the 0.55. If I could listen this one to 0.1 or 0.2, okay, much more that my electric bill will be lesser. The power factor is 0.62. So the given parameters, if we try to operate there, is cleaner here. That was in my last long video format. The true power consumption is actually 41.7 watts. If we try to operate this one on 120 volts and 60 hertz, the total current the total true power, the wattage is 41.7. Capital letter S is actually represent apparent power. What comes out for this one is 66.7 volt ampere. This is now a real example, okay? And the power factor is 0.62. If you try to notice this 0.62, this is very low. Okay, this is very low. And actually, we could remedy this one. We could increase this one to a value we would like. It could be 100%, 1. It could be 95% or 90%. It depends on what we want. Okay? So the requirement for this illustration here is fine. C, capital letter C, equal to increase the power factor to 0.95 and reduce the current consumption. Meaning to say, with this given circuit here, I would like to increase this 0.62 to a value 0.95, right? If I could raise this 0.62 to 0.95, of course, my current consumption will be lesser. Okay, so the problem is, what will be capital letter C equal to? Capital letter C equal to. And AC circuit, capital letter C is actually capacitance of any capacitor. And the unit of this one is microfarad. This symbol here refers micro. And the equivalent of this in terms of number is actually 10 to the negative 6. Okay? So, just in case you will compute for the capacitance, the unit will be with the multiplier 10 to the negative 6. And that is designated by this micro symbol here. This symbol here, okay, is micro, and that is actually equivalent to 10 to the negative 6. So the problem here is, what will be capital letter C equal to, so that the power factor is 95%. This 95% is actually very good already. It's almost 100%. And if utility companies will ever know that your power factor for a certain load is 95%, they will say to you, very good. So for this illustration here, I would like to increase the power factor of this air cleaner here from 0.62 to 0.95. And the problem is, what will be the capacitance of the capacitor needed? This is the capacitor to be needed. And what will be the value of this one in terms of microfarad? This is plug-in. It's easy to use. Okay? You just plug in this one beside the motor load which you are operating, and supposed to be, if the value is correct, you will lessen the current consumption. Okay, let's proceed. If we try to bring out the solution of this one, I will try to sit here. The solution of this one now will be an application of our knowledge of AC circuit. AC circuit. So it's a must that you should be an electrical engineer or something else. Because if you are not an electrical engineer, okay, you might not understand what I am saying over here. Okay? And electrical engineering, or in AC circuit, under study of electrical engineering, there is the so-called power triangle. For any load which is inserted in our houses, there is a power triangle for each load. For any load that's plugged in your house, there's a power triangle, and the importance of this power triangle is, by knowing this P here, Q and S, okay, we could determine its power factor and its current consumption. And the value which controls the magnitude of the current drawn by certain load is actually this S here, this hypotenuse here. So if this is big, supposed to be your current consumption is big. Okay? If I got another power triangle, okay, this is true power also, this is reactive power, and this is S. This triangle here is smaller than this first right triangle, right? Bigger, smaller. So if we try to compare this one, these two here, the lower right triangle consumes less current. Okay, less current. So to decrease our current consumption, we must have to, what you call this, lessen this hypotenuse here. And to lessen this hypotenuse, we must have to counteract some of the values here. We must have to cut some values here. If this is the original Q, you try to lessen the Q, okay, up to this height here. So what will come out will be this triangle here. So it becomes smaller already, okay. This one remains the same. So if this becomes smaller, what will come out on the hypotenuse will be smaller. And if the hypotenuse is smaller, which actually represent the total apparent power that is needed in the computation of the total current. If this is less than the original, of course the current will be less. So the way on how to, what call this, the way on how to lessen this one here is actually to place a capacitor. We must have to place a capacitor. Okay? Because for a motor load, this is upward. For a capacitor, this is downward. This is positive and this is negative, okay? So a positive and a negative will try to fight out each other. So which is bigger will be the one who will win. Okay? So if we would like that the resulting triangle will have be a small Q, we put some capacitor here to lessen this total Q here. This is big, and to lessen this one, we must have to place a capacitor. And to place a capacitor, we must have to know the exact value of the capacitor. Okay? So in AC circuit, for those who are not electrical engineers, power triangle is actually very important. This is the power triangle of the load without the capacitor, and this is the power triangle of the load with the capacitor. It's smaller now. Okay? The hypotenuse for this is actually smaller. So if we try to compute its current, of course, the current will be smaller. And if the current is smaller, okay, we reduce our electric bill. Okay, I will try to continue. So for the original circuit here, this is the power triangle. Right? It seems it is this one here. Okay? The measured true power of this one here without the capacitor is 41.7 watts, this portion. The total apparent power, is actually the hypotenuse. It is 66.7. It is 66.7, 41.7. This is known. This is known. For the meantime, we do not know this value here. Okay? So this now refers to the so-called study of trigonometry. We are given the adjacent side. We are given the hypotenuse. So we could compute for the opposite side by using Pythagoras principle. This is trigonometry. This is a right angle, right? So if we know the total apparent power, which is the hypotenuse, we know the total true power in watts. We could compute for capital letter Q with the subscript L, meaning the total reactive power of L. L is actually a motor load, L. L refers to the inductance. Okay? So if we know this one, we know the hypotenuse, we could compute for this. Because hypotenuse square equal to A square plus B square. Okay? For any triangle and the study of triangle, the square of the hypotenuse should be equal to the square of the adjacent side plus the square of the opposite side. We know the hypotenuse. We know the adjacent side, so we could compute for this. So if we try to compute for this one, which is actually Q sub L, okay, we transpose this to the left, so it will now become minus. So hypotenuse square minus B square. But that is Q sub L square. We will try to compute for Q sub L without this power to here. We'll raise both sides of the equation to the 1/2, so this will become square root. Okay? A combination of AC circuit and what we call this trigonometry already. So if we know the adjacent side, we know the hypotenuse, we could compute for this, which is actually Q sub L, the reactive power which consumes so much energy. That's why our electric field is actually very big. We must have to lessen this one. We could make this one 0 or to a certain value which is actually very negligible, so that it does not contribute to a big current passing through our meter. So we are given the total apparent power, 66.7 square, this minus the square of 41.7. If you try to use this one using our calculator, what will come out will be the square root of 2710. 2710, that's almost 25,000, so the answer should be around 50 plus. So Q sub L is actually 50.05 bars, reactive volt ampere. Reactive meaning it's the current or it's the power that gives us so much current. That's why our electric load is very big. We must have to eliminate this one totally, or we could minimize this one, so the total current that this motor will be drawing will be less. Okay? Let's try to draw the resulting triangle now. I will try to raise this one. Okay. I will reload this one, 41.7 watts. The reactive power of the motor is 52.05 bars. It is this. This is upward. And if we try to plug in this one, it's a part of the circuit now, there's also a power triangle for this one. Okay? There is no true power, but it has a reactive power. Its reactive power is downward. So this is designated capital letter Q with its subscript C, meaning the reactive power, okay, of this capacitor. We needed the reactive power of this capacitor to lessen this hypotenuse here. For the meantime, we do not know the value. Okay? So if we try to compress this triangle now, this 41.7 is still 41.7. This portion here will be 52.05 minus Q sub C. For the meantime, our power factor is just 95%. That's what the problem is asking, right? 95%. So meaning to say, the reactive power of the motor load still exists, but it is not so much because we are subtracting Q sub C. So this is upward, this is downward, so it will become 52.05 minus Q sub C, this portion here. This is still 41.7. The true power consumption of the motor does not change. Okay? So if we try to subtract this one here, what will come out will be this. The true power still exists as the same. The reactive component which remains will still be, it's lesser now, because originally the reactive component of the motor is actually very big. But it became smaller because it was counteracted by this capacitor here, Q sub C. by the addition of this one. Right? So this becomes smaller and the resulting power triangle will be less, smaller. So this is this say this becomes smaller. So if we know this one, we could compute for this. What will come out for this will be S will be smaller. The original S is actually this one here. But after the addition of the capacitor, S now will just be simply this. Since the right triangle is smaller, of course the hypotenuse is actually smaller. And that's the time that we could say that we increase our power factor and we listen this S here. Okay, this becomes smaller. Okay, if we try to operate it on the same 120, it will draw lesser current. And that's the time that we could say that the current consumption is actually less and we could save electricity, okay, by plugging in this one. Right. So this will be the overall triangle now. Okay, this is the new S. It becomes smaller. Okay. For those who are not electrical engineers, power factor is actually definition of cosine of theta. Theta is actually the angle between the true power and the apparent power. And we could compute for theta. Theta will be arc cosine to the minus 1 of power factor. Okay? The new power factor is actually 0.95. 0.95. That's the desired value of the power factor that we would like, so we could lessen our current and we save on the so-called electric bill. And if we try to compute for the angle, cosine of this angle here is actually 0.95. So if we try to compute the angle here, we needed the angle between this true power and this one, so we could compute for Q sub C. So theta to now will be the arc cosine of 0.95. And if we try to use our calculator, you just display 0.95. 0.95. Okay, second function cosine. We could get the angle. The angle between this here, this true power and this. Okay, this is again a right triangle. And we could compute for this one. And what comes out is 18.19. It's 18.19. Right? So, on the new right triangle now, this angle here is 18.19. Okay, because the triangle becomes smaller, so supposed to be the hypotenuse becomes smaller, and if the hypotenuse becomes smaller, okay, with the same applied voltage, the current supposed to be, it will be less. Actually, we decrease the, okay, I will stay here. Can you still see me? So there will be a right triangle now. This is 52.05 minus Q sub C. This portion. This is 41.7 watts. And this angle here is 18.19 degrees. Okay. So this is now the study of trigonometry for those who are not electrical engineers. This angle here is given 18.19. This is 41.7 watts. This is 52.05 minus Q sub C, this one. The overall reactive power. There is still a reactive power which remains, but it is not so much. Okay, because the desired power factor is just 0.95. So the relation between this side here and this is actually tangent. So tangent of 18.19 will be the opposite over the adjacent. It is 52.05 minus Q sub C. Q sub C is actually the reactive power of the capacitor. This refers to the capacitor. power. We needed the reactive power of the capacitor so that we could compute its capacitance. So in this equation here, the only unknown is Q sub C. So it seems we are given a trigonometric equation. Okay, so we'll just simplify. So if we try to compute for Q sub C, okay, it will be 52.05. 41.7 tangent, it is on the left side, right? We transpose it to the right, so it becomes negative now. And that's Q sub C. Q sub C, we put it on the left. We put this on the left, then we transpose the product of this to the right, so it becomes 52.05 minus 41.7 tangent of 18.19 degrees. Algebraic manipulation. So this will be 52.05 minus, if we try to compute for this one, take the tangent of 18.19, that's less than 0.5, times 41.7, that's 13.7. So 52.05 minus 13.7, the reactive power of the required capacitor is 38.35 bars. Okay, 38.35. This portion here is 38.35. The downward, this is 52.05. So if this 52 and 38 will fight each other, this is upward, this is downward, this will win, right? Because 52.05 is bigger than this. So what comes out for this one, for the reactive power that remains, will be very small. So if we try to compute for the value of C now, it is something like this. This is 52 minus 38. 14 is 6. This is almost 16. 16 bars. This is 41.7. And this is the new S now. So if we try to compute for the new S, this is only 16 now. Originally it was 52.05, but it became 16 because we placed a capacitor in parallel with the load with the reactive power component of 30.35. And this value is around 16 bars. So if we try to take the square of this plus the square of this, what will come out of this one will be less. It became smaller. Oh, that's this, what you call this, the explanation of the power triangle. This became around 16 only, this is 41.7, so if we try to compute for this one, it will be less than what you call this, the original 66.7. Okay, for those who are not electrical engineer, for capacitors, we needed this formula here. I think if you try to go back to physics, okay, there's the formula, charge on any capacitor will be the product of 2 pi f times its capacitance times the square of its applied voltage. So if we try to compute for C here, okay, C now will be Q over 2 pi f times the square of the voltage. So this is actually a general equation on how to compute for the capacitance of a capacitor needed for power factor correction. This will not change. So I place it here. This is a general equation. So this is now just a matter of substitution now. 38.35, 2 pi f, the frequency of the AC source is 60 Hertz, is 60. And the applied voltage, we are here in the USA, the applied voltage is 120, so this is 120 square. So if we try to simplify this one, this will be 38.35. The product of 2 pi f times 120 square, it will become 5.4286 times 10 to the 6. This is a million, 10 to the 6. Right? So if we try to divide 38.35 over 5 something, that will be 7 something. what comes out is 7.06. And this times 10 to the power 6 will go up. So the exponent of the answer here is actually 7.06 times 10 to the minus 6. And this is referred to as microfarad. If we see micro, the multiplier will be 10 to the negative 6. So according to our computation, the required capacitance of the capacitor to increase the power factor from 0.62 to 0.95 will be 7.06 microfarad. The symbol for micro and AC circuit is this one here. That's micro. Capital letter M is farad. We needed a 7.06 microfarad capacitor. So if we try to buy this one, we should be buying a capacitor very near this value here. Very near this value. I've gone to Amazon the other day. The nearest capacitor that they are selling is actually 7.5. So I bought a 7.5 microfarad capacitor, 400 volts AC from Amazon. So that's the one I'm using on my air cleaner now. Okay. The air cleaner is down, right? Okay. So the required capacitor now will be 7.5 microfarad, 400 volts AC. And you could do it like this. And what I did yesterday, I will try to show you. This is the capacitor. Okay, this is the plug. So on the air cleaner that I'm using, I will plug in this one beside the outlet in which that air cleaner is, what you call this, operating. And I could reduce the power factor from 0.62 to 0.95. And the value of this one is 7.5 microfarad, 400 volts AC. So this is safe inside. This is safe. Because this is very dangerous. If you try to touch this one, if this capacitor got a charge, you will be electrocuted. So what I did, guys, I put a 1 million ohms, 1/2 watt resistor between lines number 1 and number 2. So if you try to remove this one from the plug, the charge across these two lines here will be gone, because there is a bleeder capacitor which has a value of 1 million ohms. Okay, assuming there is a voltage stored on the capacitor of 120, but I put a load across it of 1 million, that current is very small, and it keeps circulating till the charge on the terminal will be 0. So this one now will be safe to touch. Okay. Just in case you're not sure if there is a charge, you'll get a, what you call this, screwdriver. Of course, this is insulated, and try to short this one. So as you could see it, there's no more spark, no more charge across this line. So we are safe to touch this one. No more charge, because I place across the line number 1 and number 2 a bleeder capacitor or resistor of 1 million ohms. And that's for safety. So this is the one I'm using now to improve the efficiency of my air cleaner, in which the original current is 0.55, original power factor is 0.62, and I got my meter there. I put that in my other plug. The power factor is actually 0.92. It's not 0.95 because supposed to be, if we use 7.06, it should be 0.95. And since I bought a 7.5, of course the power factor will be different, but it's very near 0.92. And what comes out is, by using 7.5, the power factor of my air cleaner now is 0.92, it decreased in current from 0.55. Actually, the current will be lesser, okay? Because the power triangle is smaller. This is smaller now because we counteract some by using a capacitor. Still the same, this is very small, so this will be S. Actually, the total consumption of this one now is 0.35. So this is the circuit with the power factor capacitor placed. This is the air cleaner. I put in parallel a capacitor, the one I'm showing you. Okay. This portion here is this. So it since we got two loads, air cleaner and capacitor, the reactive power of this one is counteracted by the capacitor. They try to fight out each other, so the total current drawn now will be less. And actually, if we try to compute for the current after the addition of the power factor, it is 0.35. From 0.55 to 0.35, actually, if we try to compute the percentage, it's 38% lower. Okay, that's it, guys. So, this topic of mine is good for all home users. If you try to listen, okay, or reduce the total current consumption of a specific load. Because the one I'm telling you, this is just a plug-in capacitor. If you got a motor load, compute for the required capacitance, and plug in this capacitor beside that load, we could reduce its current. And of course, if we could reduce its current, our utility bill will be less. So this is with a specific purpose. This is for a single load, which is plugged into our houses. For motor loads, standalone motor loads. If we know that the current consumption of that motor load is big, you could try to follow my lecture here, compute for the required C, and do this one, plug in this one beside your standalone motor, and for sure your current consumption will be less. And your power factor will rise up. It depends on what you want. Okay, 90%, 95%. But for this example here, what my computation says is I want the power factor to be 0.95. There's still a reactive power by the motor, but it is not so much. It's smaller already because some portions is actually being fight out by the capacitor. Because the reactive power of the motor and the capacitor will try to antagonize each other. So what remains for the reactive power will be the bigger one. Okay, and since the reactive power of the motor is bigger than the capacitor, this is very small already. So if this is very small, this remains to be the same, the hypotenuse will be less, and this is needed in the computation of the current. If the hypotenuse is less, the current will be less. Like this one here. This is a big triangle. This value here is bigger than this. Okay, you see the difference? This big triangle, this is the hypotenuse. The smaller triangle is this one here. And this represents bigger current than this one here. That's power factor correction. Good afternoon from Los Angeles. This is Professor David J. Telosue. Good afternoon.